Yeah, that's what it was.
Yeah, no, it's fine.
Yeah. I'll try. I'll do page down. Thank you. Yeah, I find that kind of difficult. And when I was preparing this presentation, I read the daily newspaper on a Saturday. Actually, I read the Saturday magazine of this newspaper. And I stumbled on this column by Jasper van Kuijk. And Jasper van Kuijk is not only a journalist and a columnist, he's also an innovation scientist. And for making his point in that particular column about maakevolutie and the evolution of making things, he needed to point out that in the beginning, we all made our own tools and used them to produce things that we needed. And then a bit later, and I think it must have been the agricultural revolution, there came a split. Some specialized in making things, and others specialized in using things, which was fine until we hit the Industrial Revolution, where we split the making of things again into a design phase and a production phase, so that some people got specialized in designing things, and other people got specialized in using or consuming things. And so the consumer and the maker got split, and there was a system in between. And this was kind of hard. And when I read this, I thought, well, he must be talking about EUSES. It brought me back into, well, where did it start? Well, we all know it started with Don McKay in, I think it was around 1980, 1983, I guess was his publication about calculating sagacity. May have been 1982 when I did my PhD, when most of you were born. He sort of set the scene in using multimedia phase models in order to predict exposure and impact of chemicals in the environment. And somewhere 10 years later, this got remade by Jasper at RIVM, and he sort of created a tool that he himself used. So he was still the beginning phase, producer and user in the same hand, and everything went fine until they got to make EUSES. And then Jasper became the maker, and others got to be the users. And initially, Jasper used it himself, but then soon thereafter, others began to use what Jasper made. And that was no problem whatsoever, but immediately thereafter, we created EUSES. And then Jasper became the designer, and the system got to produce the tool that was used by others who were then reduced to be consumers of the material that came out of the EUSES, and then said, well, okay, that means the chemical can be used safely. Which I think is a problem that we should keep in mind whenever updating EUSES. What is EUSES about? Well, if as written down by Kees van Leeuwen in this, I should say, famous red book, EUSES is basically carrying out the PNEC concept. PEC meaning predicted environmental concentration, and the the idea as written down in the first chapter of this book is we have a chemical and we have properties of this chemical and other facts about the use of this chemical that we can use to make an exposure assessment. And this then leads to the famous predicted environmental concentration PEC. And if you do this by a model, then it has an outcome. Yeah, 42, I read in your eyes. Well, it has an outcome, and it is meaningless until we compare it to something that we know is useful, safe, or the goal, or whatever. And that became PNEC. The same mass of data that we have about chemicals was used to derive a concentration that we could live with. And we called it no effect concentration. At that time, let me put it this way. At that time, toxicologists believed there was a thing like a no effect concentration. A concentration below which the effect is zero and above which effects begins to rise. And we thought if we can derive this no effect concentration for ecosystems and we can remain below this, then we are safe. And so it happened. But the difficulty was in assessing PEC and PNEC and comparing them PEC with PNEC is that at that time it was known that PEC is not one value. And in reality, if we have a chemical and we produce a certain amount of it and we use it in various uses, then as a consequence, concentrations in the environment will begin to appear. And if you do this long enough, this is going to be steady. And then there's exposure concentration that differ from place to place, from time to time, and from situation to situation. Generally, from what we do by measurements and what we do by experience, we know that concentrations of chemicals in the environment are log normally distributed. So asking, does PEC exceed PNEC? What do you mean, PEC? Well, quite generally, the majority of the PECs may be lower than the PNEC, but a certain fraction of it is greater than the PNEC. Well, this means then that there exists not a situation like PEC is below PNEC. A fraction of PEC is below PNEC, and a fraction of PEC is above PNEC. That is, if PNEC is one value. Now, at that time, we knew already that PEC is not one value either. In fact, every species has another PNEC, another no effect concentration. And there is a distribution of no effect concentrations. And that was then called the species sensitivity distribution, written down in this other famous book by Leo Postuma and his colleagues. The basic principle is that if PEC is a distribution and PNEC is a distribution, there is a certain given resulting probability that PEC is greater than PNEC, or that PNEC is smaller than PEC, which is the same. And this probability was, back in the beginning of the SSDology, called potentially affected fraction of species. There is a certain fraction of all species that are so sensitive that their no effect concentration falls below a certain concentration that we find in the environment. And this was later called toxic pressure. But what it is the probability that one distribution, the exposure concentration distribution exceeds the effect concentration distribution. And it can be worked out mathematically, very precisely, very robustly, from what is called a convolution integral. And this was in 2002 in this SSD book, written down first by Nico van Straalen and one chapter later by Straalen-Aldenberg. And I propose to honor these people to call this the van Straalen-Aldenberg integral. And I think we ought to have started EUSES right there, using the Straalen-Aldenberg integral to work out the probability that PEC exceeds PNEC, instead of demanding that PEC should be lower than PNEC. This is how it went. EUSES did PEC and PNEC and worked out the quotient of them and called that the risk characterization ratio. And it's the result of assessing an exposure concentration PEC and an exposure concentration PNEC and demanding that PEC divided by PNEC should be smaller than 1. And I hope that we will take this opportunity of updating the EUSES to return to the original meaning of PEC and PNEC, and saying, well, should we not work out the probability that PEC exceeds NOEC? In fact, we do that already because NOEC is really the 5th percentile of the distribution of NOECs. So that if we say that PEC exceeds NOEC, we really mean that PEC exceeds 5% of the NOECs. So really, we do it already. We say we work out the probability that PEC exceeds NOEC is smaller than 5%. I propose that we continue doing this and work this out for any useful effect concentration and work out the chosen probability level that we should not exceed in order to have a chemical that you can use safely. Getting back to what we learned from the past. Exposure concentration, well, it all started with the unit world concept, which I thought was invented by Don Mackay, but which Don Mackay himself, as he told me personally, was invented by George Bachman at the United States Environmental Protection Agency Environmental Research Lab in Athens, Georgia. And this is a laboratory that I had the honor to visit. Actually, I had the honor to spend a sabbatical year in, working with all these people that George Bachman had collected in this laboratory. All these famous environmental chemists like Lee Wolf, Richard Zett, Ray Lassiter, Larry Burns, Sam Kerkhoff himself. And Don Mackay worked out this unit world concept, saying, well, what is the unit world concept? The basic idea was, well, if we want to evaluate chemicals, we best put them into the same experimental environment to work out their concentration. And this became not an experiment, but a computer experiment doing the unit world model. And this is how Don Mackay worked it out. At RIVM, we worked out the very same thing, and then in other laboratories around the world, the same thing was worked out slightly differently, but as Christina Cohen collected all these people, and they concluded in their book in 1995 that all these models are deceiving. They mean to do the same, and if they actually feed them with the same information, they actually do the same. Plenty of other improvements made to this concept in simple treat, as we saw already, EUSES. One particular event was that around 2006, there was a group of people led by Martin Scheringer in Switzerland. Well, actually led by Don McKay, who thought, well, if we are to produce useful things that should be known about the chemical, like long distance for the traveling potential, overall persistence in the environment, how are we going to do this? Well, use a model, and use a model as simple as possible, getting us back to the principle of parsimony. Hi, Joris, come in. So here came various people from around the world using their own multimedia fate models, thinking about how can we calculate something like overall persistence in the environment. And the answer was, well, let's make the model as simple as possible. Don't put in any things that you don't need to make the point of modeling. And this became what's now known as the OECD tool, the Swiss tool made by the Swiss. There's two things that I learned from the past. First is the unit world concept itself. We should compare different chemicals against the same unit world in order to make a fair comparison in policy terms to get a level playing field. And this model should be as simple as possible. That's the second lesson that we learned from the past. This group of people learned that concentrations that we should expect in the environment are always directly proportional to the amount of chemical that we use, the amount of chemical that we emit, actually. But if the emission is a certain fraction of the amount that we use, then the concentration in the environment, the peak, is going to be directly proportional to the tonnage, the EU tonnage. And this proportionality constant we can work out with this unit world model. It is a function of the properties of the chemical and the properties of this unit world environment. And once these are set, then the proportionality between tonnage and concentration is set. And the main lesson from this, of course, keep it simple. What did we do with the EUSES? Well, in 1992, when we created the EUSES was not simple anymore. It was made out of simple box, and the criticism about it was that simple box wasn't simple at all. It was a not so simple box, and EUSES was even more complicated than this box. And in 2003, when we did the update and we created version 2, we didn't return to the simplicity, but instead we made it a bit more complicated. And now, come 2018, I would call on you, say, well, let's do this again and return to the full simplicity. Perhaps back to the unit world. Keep it simple. In assessment, we talked already about that. Well, in 1992, we thought that we should compare text to PNEC and thinking about one value comparing to another value, even if it's a distribution comparing to a value, we can work it out. The spec is smaller than PNEC. And in version 2, we didn't change a thing about this. Now comes 2018. I would hope that we would return to the originals, work out the probability that PEC exceeds PNEC, and work from there. This would make things a lot simpler, better. Well, where are we now? 2014, well, was Christmas 2014, I remember. Then RIBM produced this report, getting all recent developments in multimedia modeling together and presented them to ECA as recommendations for how the next version of EUSES should be. At the same time, the simple box model was updated by RIBM to become simple box version 4. Simple treat model was updated by RIBM to create simple treat version 4. Completely coincidence that these models have the same version numbers. And in 2015, the Umweltbundesamt in Germany asked us to create a model version that looked very much like the unit world model version in order to do their local assessments of chemicals with. And so this was sort of an experiment to create a very simple version of simple box and simple treat. We called it a simple square box treat. And this was actually used in their decision support system, EUSES. I haven't seen any publication about it, but this is what I would recommend how EUSES, the next version of EUSES should look. It's like this. We reduced the simple box to a 3-compartment system, air, water, and soil. Combined it with simple treat to create a simple unit world system like this, in which we can calculate release fraction of the chemical, the exposure factor of the chemical, and the effect factor of the chemical. And the product of these three is the proportionality constant between concentration and between tonnage and impact. All thanks to this marker. Actually, it's all thanks to Don Mackay, who taught us about this monk. Simply says, well, it's a philosophical principle that was developed in the 14th century already. If you have more than one explanation of an observation, the simpler explanation is usually the better. Or saying the same thing in other words, the more assumptions we need to make about reality, the more unlikely the explanation of it becomes. Don Mackay formulated it in a third way that, well, more things should not be used than are ultimately necessary. When given several options of doing the same thing, the simpler one is the one of choice. For the EUSES update, this means simple is best. And well, this is just an acknowledgement of all these people that I've worked with over my life. And I've forgotten several hundred, I think, but these are just